All right, so we're going to be doing 6.1, which is Introduction to Vectors. And in the vectors unit, we'll be looking at geometric vectors as well as Cartesian vectors. But right now we're going to be starting with geometric. So to start, we have to know what magnitude is. And magnitude is simply, it's how big something is, or its size. And so when you're looking at some physical quantities, they can be expressed by a magnitude alone. However, there are some that need more than just magnitude, and they also might need a direction. So how can we represent this? It can actually be represented through vectors. So when we're looking at some of these terms, and actually before we start, there is a template posted, which is right here, and it has some of the additional writing. So if you want to print that, if not, you can just add it to your notes. But when you're looking at vectors, there can be a difference between vectors and scalar. So a vector is the quantity between both magnitude and direction, where scalar is just magnitude. So some examples of a scalar versus a vector. If you were to look at the velocity, we could go, for example, let me switch my pen. So a scalar versus a vector. A scalar could be a velocity which might be 10 kilometers per hour. And so that is just a value. It can have units or not units, versus a vector, which could be 10 kilometers per hour. And as soon as you add a direction, so you could say south or 60 degrees from the horizontal, but as soon as you add that direction, it becomes a vector. There are more examples of these as well on page 304. So if you want to look at those, you can take a look at those. So there are different ways to represent a vector, and one might be the words. So for example, you could say 5 kilometers at an angle of 30 degrees from the horizontal. And you can also represent that then in a diagram. So if we're to get an arrow here, we're to draw a vector. Okay, so the dotted line would be the horizontal, and then the straight solid black line would be the vector that we're considering. And so it would be 30 degrees from the horizontal, so this would be 30, and it would be 5 kilometers from that. Now, that would be the geometric representation with the diagram. We could also represent it with symbols, so I'll do the symbols in red. And so that would be calling this vector A, B. And because we're looking at a vector, we draw an arrow. Some people do full arrows. You can also represent it from just doing A, B, and then just with half the arrow, and it will mean the same thing. So if we label A here and B here, that would be representing it using symbols. And another symbol that we could do is if you wanted to label sort of the entire vector, it would be using, for example, the letter U or the letter V, and that will be saying the whole thing and labeling it here as U. And so if you remember back to some of the trigonometry, when we label sides, or the vertices, sorry, we would use capital letters, and when we do this whole edge of it, then that will be using lowercase. And so that's how we get the upper and lower cases. And continue on, just as a note that when you are using trying to find for the magnitude, if you're trying to find the magnitude of the vector we just drew over on the other slide, use the absolute value lines to denote that you're finding the magnitude. So those straight lines on either side of the vector will be getting the size of it, how big it is. Also, the direction is always, when you're finding it, moving in a counterclockwise with respect to from the horizontal, just like we did on the other side as well. So now we can represent these vectors in two different ways. And this is more for the navigation, sort of giving direction. So there's these two types. One is the true bearing and one is the quadrant bearing. And so first, if we look at the true bearing or simple bearing or azimuth bearing, here's some different facts that we can look at. It's a compass measurement. The angle is measured from north. It moves in a clockwise direction. A 3-digit number, including the leading 0. And so here are some examples where north would be 0, 0, 0, east would be 90 degrees, south would be 180. Now when you're looking at that, those are basically just the vectors on here, like so. So there's 0 degrees, 90, 180. Okay. And so we could even have an example in here where we have, for example, a 45-degree angle. And so all of those would be a true bearing, like this, 45 degree. And those it would just strictly be the angle. And as a brief example, if we were given, so we have north, east, south, west, if we're given an angle of, let's say, 150 degrees. So if we had that 150 degrees, the true bearing on this graph would be down here, and that would be from here to here, which is 150 degrees. And now for the quadrant bearing. A quadrant bearing, it is measured between 0 and 90 degrees east or west only. All right, sorry, my phone keeps ringing. So it's between 0 and 90 degrees only, and it's based on the north-south line. So all quadrant bearings are referenced to the north-south line only, and there are always three components. The first component is if it's north or south direction, then it's the angle, and then it's the direction towards which it's going. And so as a diagram, if we look at the angle that we just did on the previous slide as a true bearing, so we have here, we have our north, east, never eat shredded wheat, if any of you can't remember it. And so from here to here, that was the 150 degrees, which gave this vector right here. So now if that's the true bearing and we had to get the quadrant bearing, remember it's always based, so I'll do the quadrant, I'll do it in green. It's always based on a north-south line. So if we're going to base it here on the south, we have to figure out what this is. Well, if we're going to complete the line, that means that this has to be 30 degrees because a straight line is 180. And if you're going to say that as a quadrant bearing, we went south and then we go 30 degrees east because we had to go in the east direction. And so that will be the quadrant bearing. Now finally, we have some additional terms that we have to go over. And the first one is parallel vectors. And so let me just go down. So they have either the same or the opposite direction, but and not necessarily the same magnitude. However, they have to be, and again, you guys know what parallel lines are. So if we were to draw a trapezoid, for example, and clearly I've drawn this to scale, this line and this line could be parallel vectors. And we could even label them. Let's say we labeled it A, B, C, D. We could say vector A, B is parallel, which we can denote this way with two lines, to C, D. And those two would be parallel vectors. The next one is equivalent vectors. And so if I were to create a vector here, like so, and then I wanted to duplicate it, I could, there it is over there, those would be equivalent vectors, which simply just means that they have the same magnitude, same size, and same direction, but the location of it doesn't matter. So the vector could be over here, and that's okay. The last one is opposite vectors, and opposite vectors have the same magnitude, but opposite direction. So I'm just going to get a vector and draw it like this, and I'm going to get another vector, and we'll go again this way. Now these aren't exactly the same. They should be exactly the same magnitude, meaning the length of them, but they are both in opposite directions. So this could be said, for example, as if it was AB, the opposite would be the negative AB. And so there's your additional terms, and there's a mind map that you'll be doing as well as some additional questions in class, and that's it.